honors presentations of the year. It's my pleasure to introduce our speaker today. I'll start with a little story, because we maybe talk too much sometimes, but a few years ago, I think it was Leslie Quache contacted me and said that there was a new student in the STRONG program interested in computer science and astrophysics. Wondering if we could come up with some kind of project. Now, usually I have a hard time coming up with projects for first-year students, but it quickly became clear that he had an uncommonly strong background in programming. So I thought we should give it a shot, and we started meeting once a week just to talk about algorithms, to talk about the basic meat of how people do computational physics. And a pattern started developing, actually two patterns started developing. One was that meetings that were supposed to be 1 hour in length repeatedly turned into 2 to 2.5 hour long meetings, just because we were having so much fun talking about algorithms. And the other pattern that started developing is at the end of every meeting, I suggested 2 or 3 more algorithms that he should study up on and try to implement. And week after week after week, every damn week, he was accomplishing 2 to 3 times as much as what I thought would be possible. At any rate, at that rate, it would make sense that someone would quickly become an active researcher in numerical relativity. And indeed, the work that he's presenting today is work that he's presented 2 times at annual meetings of the American Physical Society in 2 different stages of development. At the end of these introductions, we usually talk about where the student is planning to be in the fall. I can announce that Iago will be spending the fall in the esteemed institution of Oberlin College, because he still has another semester to finish before we'll let him go. But this summer, he will be working in what I personally consider, in my biased opinion, to be the best research group in the world, because it's the research group that I came from, the Theoretical Astrophysics and Relativity group at Caltech. After that long introduction, I've eaten up some of your time, I'm sorry, but let's welcome our speaker today.
Wow, thank you so much for that kind introduction, Rob. And thank you everyone for coming to this talk. I'm really glad to see so many people here. I'm also hoping that many people back home are watching over Zoom. Today I'm going to be talking about the research that I've been doing for the past 3 years under the guidance of Rob Owen. So without further ado, let's get started. This is kind of the setup that I have for this presentation. First, I'm going to introduce the field of research that I've been working in. Then I'll kind of try to introduce the concepts behind the research that I've been conducting. Then I'll get into how we solve the problem that we intend to solve, along with the codes that we developed in the process. And then we'll finally apply our solutions to simulations of binary black hole mergers. For my non-specialist friends in the audience, I would advise you that this is a technical presentation. But even so, I would ask you to hang on even in the speed here on the most complicated part of the talk, because we're still going to go down and we're going to see some nice animations and everything. So in the early 20th century, Einstein revolutionized the understanding of gravity. He, instead of describing it as a force, he described it as the manifestation of geometry of space-time. And there's this famous quote here from John Miller, who I'm proud to say that he's kind of my great-grand parent in the academic world because of being the advisee of Rob. And he says that space-time tells matter how to move, and then matter tells space-time how to curve. And because of being such a complicated theory, many times it's hard to develop analytic solutions to the Einstein field equations. And this can only be done in cases with high symmetries. But of course, we don't live in a very symmetric world. We have many more complicated situations that we find in nature. And so in order to simulate those scenarios, we need to use numerical solutions. So this gave origin to the field of numerical relativity. And the basic goal of this field is to use big computers to solve GR problems. And this became a very important field, especially with the development of detectors for gravitational waves. And specifically, these detectors really need simulations of black holes. So here is a famous picture from the first detection of gravitational waves by LIGO in 2015. And here on the top, you can see data that they got from their detectors. But in order to say that the data that they detected was actually from a binary black hole system, they had to compare it with data from numerical relativity codes. And in this case, they used the code from the collaboration that now I'm part of, called the SXS collaboration. Here's an example of what a simulation like this can look like. So here is actually the simulation that was used in the previous slide. We have two black holes orbiting each other. We can look at their position in 3D space. On the bottom here, we see a two-dimensional representation of what the fabric of space-time can look like. And then from this simulation, we can extract the gravitational wave data. And then here, they are about to merge. And at this point, the movie is frozen just for a little bit. And then they enter what we call the ring-down phase. So this is what a simulation of black holes look like. Here I have a specific frame of that same simulation. And in this talk, I'm going to be focused more on the description of these black hole surfaces. And more on that later. Now, before talking about the actual research that I've been conducting, I need to give you a little bit of an introduction to differential geometry. And as I mentioned before, Einstein uses geometry to describe gravity. So we need to be able to differentiate and compare geometries. And this is what we use the field of differential geometry for. And in order to do that, we need to find some intrinsic property of geometries. And it turns out that this property is the distance between nearby points. And the way that we do this mathematically is with what we call a line element. So a line element basically consists of this equation here, where the s is nothing more than the distance between any 2 points, and dxa and dxb here are just our distances in each coordinate. The connection between those coordinates and our infinitesimal distances is given by this GAB here. This is what we call the metric tensor, which for our purposes here you can just think of as a matrix. And I'll commonly refer to this mathematical object as just a metric. And the key idea is that given a metric, you can describe anything that you want about a given geometry. Now, I know that if you're seeing this for the first time, you may be like, wait, how is this actually done? So let's look at some examples. First, a very simple example, the Euclidean plane. We know that we can describe the Euclidean plane using rectangular coordinates, x and y, or we can also use polar coordinates, which I'm calling r and phi. We can create these triangles here, and of course, as we look at infinitesimal distances, the Pythagorean theorem works still. And with this, we can create the line elements for that geometry. And so here I have the line element for the rectangular coordinates, and here I have the same line element for the polar coordinates. And from this, we can then find out what is our metric. And so here, 1, 1 just means that here on the front of this element we have 1, and here as well, and here we have r, that's why that one has an r squared there. Okay, but this one is maybe too simple. So let's look at a little bit more complicated case. It's the surface of a sphere. And again, you can use the same idea. Here I'm using the usual theta and phi spherical angle coordinates that we are using in physics. And with a little bit of geometry, it's not that complicated. You can again come up with expression for the line element for that surface. And again, this gives you the metric for that geometry. Having the metric, we can actually find important stuff about a given geometry. For example, with a little bit of some arguments, you can describe that the area element of a given geometry is given by the square root of the determinant of that metric. And here I'm using that same metric that we just saw for the sphere. And so you can then figure this out, and then your area element is just the r squared sine theta d phi, which is a famous result from multivariable calculus, of course. And then if you just integrate this area element, you get the usual 4 pi r squared formula for the area of a sphere. So we already know this result. So let's look at geometry that maybe we're not so familiar with. And that's the curve horizon. This geometry describes the surface of a black hole that's rotating. And the rate at which the black hole is rotating is called the spin, which here I'm calling chi. And I'm not going to justify the line element. I'm just going to tell you that this is the line element. Having this line element, you can then figure out a lot of important things about the geometry. Using the same arguments that we used in the previous slide for the area element and then integrating it to find the area, you can figure out that this is the area as a function of the spin of the black hole. And if we actually plot this area as a function of spin, we see some interesting properties of the geometry. For example, if we have no spin, this means that we just have a sphere with no rotation. And this is what the Schwarzschild geometry gives us. And it predicts that we're going to have a black hole with 2 m of radius. And here, m is equal to 1 in this example. And so if we just take 4 pi 2 squared, this gives you the 16, which is what we have here in this plot. And from the plot, we can see that as we increase the spin rate, the area of the surface area of this black hole decreases, which is actually a property of the poles contracting as it rotates, but the black hole actually keeps this equatorial region constant. So look at this. Let's reflect a little bit on what we did. We just used one equation, the metric of this geometry. And with that, we were able to describe many things about that geometry that's so weird for us. And the main takeaway from this is that this metric object carries a lot of information. And once we have such object, we can then explore many different properties of our geometry. Now, in the title of this presentation, I have this maybe complicated word here, isometric embedding. So what is it actually asking for? So the main idea for the isometric embedding problem is that we want to visualize some surface in 3D Euclidean space, that is the geometry in 3D space that we are used to for describing with x, y, and z. And we want to find some representation of, in this 3D geometry that has the same properties of some other 2D geometry. And I know it's a little bit complicated to just say in words, so let's look at some visualization of this. For example, we know that the Earth is approximately spherical, right? Hopefully no flat Earth. And if we look closely at the Earth, of course we approximate it as a flat plane, but if we actually measure some distances around the Earth, we can actually figure out that it's a sphere. And this was actually done a long time ago. And it's the same idea that we have here. Using these distances in this given geometry, which is given by the metric as we just looked at, we can then figure out a representation of this geometry in 3D Euclidean space. And so this isometric word means that we're keeping the same metric as the desired geometry. And the reason why we choose the 3D Euclidean space is that in this geometry we have a preferred coordinate system. It's much easier to represent geometries in 3D Euclidean space using x, y, and z, because then we understand how the shape of this object looks like. And I'll come back to this idea in the end of the presentation. So, mathematically, to solve this problem, or to set up this problem, we need to use the line element for a general sphere, or a general surface, sorry. And here, this surface is going to be described by whatever metric we have as input to our algorithm. And here, again, I'm describing the surface using the usual theta and phi spherical angles. And then here we have the line element for the 3D Euclidean space. Now, our idea is to find what are the x, y, and z embedding functions, and so we can just expand those differentials in this format. And then by just plugging in these in these two equations here, we want the infinitesimal distance to be the same. We can just arrange the equations, and then we arrive at what we call the embedding equations. So this is the system of differential equations, or should I say the partial differential equations that we want to solve in this research. And using what we call index notations in GR, we can rearrange these equations and just write them as just one line. But this just represents still the same three equations as before, where here I'm letting A and B be either theta or phi, just like before. And solving the system of PDEs has been known to be difficult since the beginning of differential geometry. And specifically because of the quadratic order derivatives here that we have, this cannot be solved using usual PDE algorithms. And that's why I'm talking about the research that we've been doing here. Now, some motivations for solving this problem. Maybe the most easier one to convince you of the motivation is that in 3D Euclidean space, we have a preferred coordinate system, as I said before, x, y, and z. But as we're going to see later, in the simulations that we just looked at for black holes, we're talking about a curved geometry. It's not a flat geometry anymore. And actually defining a preferred coordinate system in such geometry is not as easy as it is in Euclidean space. And by using a representation in 3D Euclidean space, you remove this arbitrariness when visualizing the horizons of the black holes. And apart from that, maybe some more physical motivations for this problem is to actually compute important quantities like quasi-local mass, energy, and angular momentum for black holes. Now, that being said, not all geometries can be embeddable. And a famous example of this, or famous for people in the field, is the same curved horizon that I was describing before. And if we actually keep increasing that spin rate of the black hole over this limit here of approximately 0.87, it actually cannot be embedded anymore. And a way they can use to understand this is that the poles become flatter that you can actually represent in 3D Euclidean space. Another remark to be said is that these embeddings are not completely unique. So basically, once you find some representation of the surface in 3D Euclidean space, you can still translate it or rotate it in any way, and that's still going to be a valid solution to those PDEs that we just talked about. Now, that's the setup that we are working with. How do we actually solve the problem? We actually solved it in two different ways. One is what I call here the matrix method, which was actually mostly worked on by an Oberlin alumni, Henry Zhu, who is actually a grad student at Princeton. And the other one is the one that I've actually been working with the most. So first I'll briefly introduce the work that Henry did, and then I'll move on to the second one. So the main idea for this matrix method is that, and by the way, this was adapted from another scientist in our field. The main idea for this method is to use what we call pseudospectral collocation. Now it's a fancy name, I know, but the main idea for this is to represent those embedding equations, x, y, and z, as an expansion of basis functions. And for anyone who has taken modern physics, we know that the spherical harmonics represent a complete basis. And so we can just use the spherical harmonics to expand our functions, and then using this, we can replace any derivatives of our embedding functions by analytical expressions, because we know how to work with spherical harmonics really well. And so the only thing that remains is for us to figure out what are our spectral coefficients, which here I'm just calling DIN. And we do this by using a Newton-Raphson method. And at each step of the Newton-Raphson iterations, we need to find how to update our spectral coefficients. And this turns out to just be a big matrix problem. But that's not a big problem, because we know how to deal with matrices. We have a lot of old codes that can deal with matrices really efficiently. And so we just have this big matrix here where this and this is known, and we just have to find our d delta b's. And that's it. And to solve this matrix problem, we just use this Gelsi routine, which is from the LAPACK package. Now, let's move on to the second method. Oh, and I should have mentioned before that this method that we use here for solving this matrix problem, the issue with it is that it doesn't scale well with resolution. And this is what motivated our second method, which I'm calling here the relaxation method. And this was some genius idea that Rob had over a summer. He got really excited to tell me about it. And the key idea of this method starts right at the foundation. So instead of finding the embedding functions, we first try to find the basis vectors of our surface. And so here we want to find what are our E theta and E phi, and I'm just calling them here by EA, just like before. And these basis vectors, as we all know, they are related to the usual coordinate representations by just a partial derivative. So that's it. And if we want to look at an example of these basis vectors in spherical coordinates, I have this picture here to make it clear. So here we know that these basis vectors always point towards the direction of increasing coordinates. And so here, if I have the E theta, it's going to point in the direction of the increasing theta coordinate, and this E phi is going to point in the direction of increasing phi. And here we're not really worried about our basis vector. So that's what we want to find. We want to find what is E theta and E phi. And I'm going to be calling those vectors the diode vectors. And here's an example of the diode vectors for the embedding of a sphere. And so here we see that the E theta vectors, they're going to be pointing along curves of constant phi coordinates. And then in this right figure here, we see that the E phi vectors point along circles of constant theta values as well. Now, if you want to find basis vectors that actually represent a coordinate system, they need to commute. And what does this mean? So imagine that you have some coordinate system, and you first decide to go along the phi direction and then along the theta direction. If you just switch the direction that you followed, so basically first go in the theta direction and then on the phi direction, you would expect to turn in the same place, right? You hope that by commuting these vectors, didn't really change anything about your final destination. But for this to be true, these vectors need to commute. And if they don't commute, you have what happens here on the right, where your final destination is going to be two distinct points. And so to make sure that our vectors commute, we define this quantity that I'm calling here the commutator. And if our vectors actually commute, this needs to go to 0. And so our idea is to make these final points here as close as possible. And the approach that we take for this problem is, okay, let's start with some initial guess for our diode vectors. And then let's just rotate them and make sure that as we rotate them, we drive that commutator quantity to 0. And in order to do this, we use a relaxation algorithm. And in this process, we need to think of the whole algorithm as evolving over time. And as time passes, we are changing our diode vectors. And this is why we have to introduce this non-physical time parameter here. And then our evolution equations, or the way that we update our diode vectors, is just like this, where our new vectors are just going to be the old ones plus some updates that we're going to apply over time. And since I just said that we're going to update the vectors by rotating them, we can introduce some angular velocity vector, omega. And then the evolution equations, which is basically describing what is the way that these vectors evolve with time, is just a cross product with the velocity vector. So if you're taking classical mechanics, you're very familiar with this. And you can also define what I'm calling here the error norm, which is basically a measure of how good we're doing. So here, what I'm basically doing is taking some positive quantity of the commutator, and I'm then integrating this commutator, or this commutator norm, over the whole sphere. And the main idea for this is that if the commutator is being driven to 0 everywhere on the sphere, then this scalar quantity E should also be driven to 0. And yeah, if we want to minimize our error over time, of course we want to drive this error E to 0. That is, we want its time derivative to be less than 1. And this is what we use to define our velocity vector, our angular velocity vector. And there's a lot of math that goes in the process. We can then express this huge double integral here in terms of some terms of our velocity vector, dotted with this quantity here. And if you want to make sure that E dot is always negative, then we can just say that our angular velocity is going to be equal to this quantity between braces here, so that this is just an inner product with omega with itself. And this, of course, is always positive or 0. And so this means that our error is always going to be decreased or remain constant at the worst case. Now, I've just been talking about making sure that the vectors commute. I haven't talked at all about solving the embedding problem, which is actually our goal. To do that, we can first use the definition of the diet vectors in terms of partial derivatives of the embedding functions, so that we can rewrite our embedding equations in just this simple form here. And with this, we define what I'm calling here constraints, CAV, which is basically just taking the difference between these two sides. Again, if our solver was able to find accurate solutions to this problem, that is, that this side is equal to that side, then this constraint should be equal to 0. We should drive this quantity to 0. And to do this, there's a lot of processes that go into this process, and if you're interested, I invite you to take a look at my thesis. But for our purposes here, I'm just telling you that this evolution equation works. And if you actually go through some derivations, you can actually show that this makes sure that our constraints are always going to be either decreased or remain constant. And here, a way to see this is that if you just say that the constraints are 0 here, then this whole term goes away, and then we just have the same evolution equation that we had before. This approach is known as constraint damping, which was developed by Rob Owen himself during his times at Caltech. Now, once we find the diet vectors, we have to, of course, solve the embedding functions, because that's what we are looking for after all. But this turns out to be not a big problem, because, as I said before, the diet vectors are related to the embedding functions just by partial derivatives. And if we just use this, we can rearrange the equations in this form here. And remember that at this stage, we have already found the diet vectors. We have already found proper values for our diet vectors. And so this right side here is known. We already know what it is. And so this just turns out to be 3 Poisson equations. And as anyone who has already taken Physics 311 here at Oberlin knows, we know how to deal with Poisson equations. And so this is not a big problem for us. This is a diagram that summarizes the whole process that I talked about for the relaxation method. We take the metric as an input to the algorithm. First, we have to find our diet vectors by applying some rotations and using this approach that is called the constraint damping. Then, this is going to give us the proper values for E theta and E phi, and with this, we can then construct the surface used by solving Poisson equations. And as an output for the algorithm, we have embedding functions x, y, and z. Now, I've just talked about math for the algorithms, but this was all done in actual codes, because that's the way that we can actually solve the problem that we're looking for. And to do this, we implemented 2 different codes, and I'm going to briefly talk about them here. The first one is what I'm calling the finite difference embedding code, FIDEC. This code was created to test the relaxation method in a separate environment. That is, we don't want to be worried that there's some other part of the code, of a big code, that's impacting our results. We just want to make sure that this method works just by itself. And this FIDEC code was written in C++, and it's open source. It's linked at the end of the presentation if anyone wants to take a look. And the way that it computes derivatives is using the well-known finite difference approximations. And as everyone who has already used the finite difference can attest, this approach just replaces any partial derivatives by analytic expressions using the nearby points. The second code, which is actually more useful for us here, is the spectral Einstein code, or for short, SPEC. This is the main code for our collaboration, and this is the code that was used to simulate that same binary black hole system that I showed at the beginning of the presentation, and this is actually what was used with the LIGO detection. This was also written in C++, and similar to the matrix method that I talked about a little bit ago, this code uses the same idea of pseudo-spectral collocation to represent any function as an expansion of spherical harmonics. And again, the same motivation here applies. Since any function can be represented as this expansion here, any derivative of f is then computed analytically up to truncation error. Because we know our spherical harmonics really well, and so everything that we need to figure out is the spectral coefficients. And so once each method was tested independently, that is the matrix method and the relaxation method, both methods were then implemented in spec. And this is the implementation that I'm using for all the results that we're going to start seeing from now on. To actually test our methods, we had to use a lot of different surfaces. And some of them are represented here. Some of them were useful to test for non-axis symmetry, like for example this ellipsoid here. Some of them were useful to test for negative curvatures, like the z-pin or the x-pin. But the one that I'm more interested to talk about here is the curve horizon, because our final goal is, of course, to simulate black holes. And so we need to understand how our method works with this analytical description of black holes. Here I'm showing you a convergence plot for the curve horizon. By convergence plot, I mean that I'm just plotting the errors on this vertical axis and then the resolution on the horizontal axis. And of course, as we expect, by increasing the resolution, we expect that our method becomes more and more accurate. That is, lower and lower errors. And here, notice that I'm using log scale on the vertical axis, and by these linear fits that I'm showing here on the plot, we can actually see that both methods are converging exponentially, which is actually expected for spectral methods like the one that spec is using. We can also look at how each method is scaling with time. That is, we increase the resolution and we see how much time it takes to run in the computer. And again here, I'm showing linear fits, and in this case I have a log scale in both axes. Because of this, the linear fit is actually telling us that there is a polynomial relationship between the resolution and the times. And from this fits, you can actually see that the relaxation method scales as approximately L to the fourth, whereas the matrix method scales as approximately L to the sixth. So there you go. We were able to develop a method that scales better with resolution than the matrix method, which was the whole motivation for the relaxation method, as I said before. Another interesting test case for our algorithms is to see how they behave at the breakdown of embeddability. That is, if you remember a few slides ago, I mentioned that these curve horizons have a limit for when they can be embedded in 3D Euclidean space. And so here what I do is I keep increasing the speed rate of the black hole and pass the embeddability limit, and we see what output we get. And so here I'm showing the results for the relaxation method as well as for the matrix method. And as you can see, before the limit, which happens over here, they agree pretty well, which is good for us. Each method uses a very different approach for solving the problem, and they find similar results. But then, after the breakdown of embeddability, each method treats the errors differently. Whereas the matrix method creates these rings of uncertainty near the poles, the relaxation method kind of tries to make the poles smooth, even though both of them are, at this point, inaccurate. Because, as I said, embeddings at this stage do not exist. We can also look at our errors as we do this process. And so here, again, I'm changing the spin of the black hole of the curve horizon, and I'm plotting on the y-axis here the errors for our methods. As you can see, once we get close and exceed this embeddability limit, our errors jump. And so this is, again, kind of suggesting that our method is indeed not being able to embed those surfaces properly. And here I'm using a resolution of 20. If I increase this resolution to 30, we actually see this jump becoming sharper and sharper. Now, I've talked a lot about codes and testing the algorithm, but I mentioned that we're going to have some nice animations, and now we're almost there. We're going to now apply both of these methods to simulations of binary black hole mergers. Before doing that, we need to talk about how these simulations actually work. And so, binary black hole, or just BBH, to simulate those BBH runs, we need to specify some initial parameters. The first one here is the mass ratio, Q, which is just, as the name suggests, the ratio between the two masses of the black holes. We also need to specify the spin of the big black hole, which is of course a vector in 3D space. And we also need to specify the spin of the small black hole, and where here is just represented as chi b. And as I mentioned early in the presentation, in general curved space, which is what we have in simulations, spec needs to choose some coordinate system, but it's not very clear how this coordinate system can be chosen. And so what spec does, it just figures out which one is going to give the most stable results numerically for the simulation. But this sometimes can lead to what I'm calling here the coordinate shapes, that is, the shape that the horizons have in a given coordinate system. These shapes can sometimes have some non-physical distortions. And I think this is a little tricky to talk about just in words. So let's look at a very, very simple example of this. So this idea of the coordinate distortion that I'm talking about is kind of easier to understand in this analogy here. So on the left, I have the r and phi polar coordinates, whereas on the right, I have the x and y rectangular coordinates. And again, this is for the Euclidean plane. So a very simple case, just for showing what I'm talking about here. As we know, in polar coordinates, we can represent the r equals 1 function as just a straight line, right? But if we then look at this same curve, but now in rectangular coordinates, this is represented as a circle, right? Now, because we are in Euclidean space, in this case, we know that x and y are preferred coordinates because the basis vectors of the rectangular coordinates are orthogonal between each other, which is not actually the case for curved geometries. So distinguishing between which one of these the code should use in curved space is actually a little bit harder, which is why we talked about this in the motivation of the project. Now, it's time to look at some nice black holes. For this in the next slides, I have a similar structure. Over here, I show the parameters that I just talked about, so the mass ratio and the spins of each black hole. On the left, I have a little animation for the black holes as they are merging, and here I'm just showing the isometric embeddings, so the results of our code. And then on the right, I'm comparing some coordinate shapes with our embedding methods, with our embedding results. And so here we see that they're orbiting each other and then they merge. It's a very satisfying video. And if we just look at some specific frames of the video, we can actually see this kind of coordinate distortion that I was just referring to. And so here, you can see that pre-merger, this was the shape in the coordinate system chosen by spec. And notice that here we have a flat region towards each other, which is actually not what we would expect. Of course, like, gravity tends to attract things. And so as they get close to each other, we expect to see some bulges, just like we see here in the isometric embeddings. And similar things happen in the post-merger results. Whereas here, by looking in this axis here, you can kind of think that there is some kind of shear force in the common horizon. But actually, once you look at the isometric embeddings, you see that they are actually pretty axisymmetric around this axis here. We can also look at a case where the black holes are initially spinning, aligned with the orbit. And we have this result on the left there. And in this case, again, we have similar results where we have this, what we call the pancake shape like, in the coordinate shape. But then the embeddings actually show that this is actually not what the metric of that surface is actually representing. Here's a very similar case to the one I just showed, but now with the spins opposite to the direction of the orbit. And here again, similar results for the coordinate shapes compared to the embeddings. This one is one of my personal favorites. This is this one we're simulating the big black hole being 4 times more massive than the other one, and we're just keeping them stationary initially, or not spinning initially. And then if we actually run the simulation, it's actually quite interesting. As you can see right there, when they merge, they have that shape there. And if I just look at some selected frames of that simulation, we can actually see the bulge effect that I was talking about being very highlighted here. In this case, look at the distortion that we have on this small black hole, which actually goes away once we look at the embedding. And this is especially highlighted in the big black hole here. And similar effects on the post-merger simulation. We can also look at a generic run, where we let this one be 2 times more massive than the other one, and we just choose some arbitrary directions for our spins in 3D space. And yeah, if we just let it run for a little bit, we have this result shown there. And again, here we can look at some special frames. And this one I found so interesting that I actually decided to 3D print it. It's actually quite nice. I also printed some more there, so feel free to grab some on your way out. Yeah, sorry, I'm a nerd. I also found this one so interesting that I decided to look at some, look at another animation of that one, where here I'm comparing the coordinate shape with the isometric embedding throughout the whole evolution. And from the beginning, you can already see some differences. Well, here, the closer it gets to merger, this small black hole here gets flatter and flatter, whereas this one still keeps its horizon pretty round. And now I'm going to replay the merger phase, and I'm going to highlight here the non-physical distortion that I'm talking about. So just compare this one with that one, and you can actually see that this one is actually much rounder than it would indicate in the other, in the coordinate shape. During these simulations, we can also see some cases where our methods fail to embed the surfaces. And this is an example of such scenarios. Here on the left, I'm showing the result for the relaxation method, and on the right, I'm showing the results of the matrix method, and this is for the empty aligned run. And why do we think this is failing? Or we think this is an indication that those horizons are actually non-embeddable. Well, there are a few reasons. First, each method was developed by using very different approaches. As we talked about, one uses this big matrix problem, whereas the other one is a totally different problem where we are relaxing the diet vectors over time. And they both find some sharp features, and it can actually be proven that this horizon should actually be always round. And so this is some of the reasons why we think that. And this is another example, maybe a more extreme case, and this is for the Q4 run, so the high mass ratio case. And this one is very extreme. As you can see here, you have some very weird, sharp features in the horizons. And why am I saying that we think this indicates non-embeddability? Well, no one ever studied how numerical horizons become embeddable or non-embeddable. And as I'll talk about this in the future work, we have some, this is what we aim to tackle in the future. Now, in summary, we have developed 2 novel efficient algorithms for solving this isometric embedding problem in SPEC. We have tested them using many surfaces, and we have made sure that they converge, and we have been able to analyze the behavior of each method. We then apply these methods to numerical horizons in binary black hole merger simulations. In the future, we hope to understand better how numerical horizons become embeddable or non-embeddable, which is what I'm calling here this critical embedding project. And we actually have some interesting ideas. We think that it might behave like the phase transition in thermodynamics or some other processes in physics, but we're not there yet. We also are hoping to generalize our methods to, instead of embedding a 2-dimensional surface in 3D space, we want to generalize it to be able to describe a 3D volume in 4-dimensional space. in this four-dimensional space is the Minkowski space, and this will be useful because some famous mathematicians, Wang and Yao, they developed a new notion of possible open mass for black holes that actually requires such embedding. Lastly, we are hoping to use our embedding results to kind of improve the way that SPEC chooses its coordinate systems in the curved space, the way that we just talked about before. And this will hopefully make our simulations faster because then by having more round horizons, we can then decrease the resolutions. I cannot end this presentation without thanking a lot of people. First, I'd like to thank Rob. He has been incredibly helpful throughout all my journey. As he said in his quick story, he helped me to introduce me to the field of numerical relativity. He took me to my first conference in physics. I'm truly very grateful for all of that. I would also like to thank Heng Mizu, who I think he's watching over Zoom, for all the help that, not only for the help that you gave me doing this research, but also for the advice that you provided me regarding grad school and in future, in my future in the physics community. Of course, I would also like to thank my family, and in specific, I would like to thank my parents in my native language. Pai, mãe, muito obrigado pelo suporte que vocês me deram durante toda a minha carreira. Eu sei que a distância pode ser difícil e também as visitas são difíceis de acontecer, mas sem o seu apoio eu não estaria aqui, então muito obrigado. I would also like to thank Oberlin College, and within this I have so many people to thank. The departments for both of my majors, my physics and CS majors, being away from my family, being here, like being an international student, it's kind of challenging, but I really felt like I was in a community between each major, and I'm really grateful for all the community that was built. As Rob mentioned, the strong program also was really important for my career. It actually helped me start this research that I'm presenting now, so I'm really grateful for the strong program as well. And with that, I thank you for your attention, and I'll be for questions.
Okay, thank you. Do we have any questions?
I didn't want to interrupt, but when you were showing the black hole mergers,
okay,
sometimes the surfaces were blue and sometimes they were orange. What is the significance of the color coding?
Thank you for the question. Yes, let's use my favorite, this one. So this is actually the Ricci scalar. I'm plotting as dark the values for the highest Ricci scalar and the blue regions for the lowest Ricci scalar. Ricci scalar in general relativity is a measure of how curved the geometry is at a certain location. And so basically you can interpret this as wherever is redder, that point to be more curved, whereas the points that are bluer, they are more flatter or like have a negative curve. Thank you.
You mentioned earlier that you're finding like the partial derivatives using a first order finite difference equation.
For the finite difference code, yes.
Yeah. Would there be a difference if you use higher order finite difference equations?
We did experiment with higher order finite difference equations, but again, this was for the finite difference code, which is not actually what we use for the final runs. For the final runs, we actually use the spectral code, which actually is much more precise than we could do with the, well, it's better for us because then we can actually run all the simulations that are already implemented in the code. So we did experiment, I think, with second or even fourth order, I believe.
Yeah, it was a while ago, but your finite difference code, the spatial derivatives were second order accurate.
Oh yes,
Okay.
that's true.
Yeah, but the time steps were first order accurate.
Yes.
Okay.
I had a question, and this might be like kind of wrong, but like with like the commutator of the embeddings that we talked about,
Yes.
is there like some way to like cook some kind of generalization of those with some like Christoffel symbols, or something that would lead to like maybe like an idea to understand the what gauge we want to use or something? Is that related, or would that totally be off?
I'm not really sure. Do you know?
This is kind of a deep general relativity question, but yes, derivatives of basis vectors are indeed related to connection coefficients or Christoffel symbols. And if the dyad vectors commute, the connection coefficients will be symmetric in their last two indices, as Christoffel symbols normally are. And so in a sense, this is the Christoffel symbol of those two basis vectors.
Any more questions? Yes.
This is a pretty basic one, but you mentioned about when the black holes are spinning, that they're squishing down vertically but not spreading out across the, like laterally. Like, how does that happen? What's going on there?
That's a good question. The way my approach to this problem is you can prove it using math, and those are the mathematical results. I'm not aware of an intuitive explanation for why that's the case. Do you have an intuitive explanation?
I apologize for jumping in, but it is an interesting answer. Basically, in general relativity, a bunch of the pseudo forces that we know of in Newtonian mechanics become manifestations of gravity. One of those is the centrifugal pseudo force, and in fact, you might think that just due to centrifugal force, the equatorial region would expand outward, and the north and south poles, I don't know what they would do necessarily. Now that's not exactly what happens here. The poles get shrunk down and the equator stays the same. And that's basically because here we're talking about black holes with a fixed mass. And as you increase the spin of the black holes, that adds energy to the system, which does its gravitational thing.
Thank you.
Yes.
How does the accuracy of the simulation's results compare as you move across the phases of the black hole merger?
Ooh, that's a great question. I wish I had the plot here. We do have some plots for that. If you want, you can take a look at my thesis, which is linked there. But it actually varies. So basically, at each point in the simulation, we are basically solving each method once. And so throughout the simulation, we can have higher or lower residuals or errors. And in general, we see that the hardest horizons to solve for are the ones close to merger. So whenever we're right before merger and also like right after merger, those are usually the hardest ones to solve, and they usually lead to the highest residuals as well. And in the cases that we see here, when we actually see some failed cases, in these results here, the residuals really jump high. But sorry that I don't have the slides here, but you can look at it in my thesis.
Clarification on that, or when you're talking about residuals, are you talking about it versus like experimental measurements from Blackboard stuff, or is it from like another theory?
But by residuals, I just mean like theoretical residuals. So the way that we define this is I have somewhere here in the here. So our residuals we define by just taking the difference between the two sides of the equation. So this is the left side of the embedding equation, and then this is the right side of the embedding equations. By residual, I mean how good our solutions are solving the equations there. And that's what we use to define our errors. So no, we are not really using the any experimental data. And I'm not really sure if that's actually possible because we don't really see this kind of.
Yeah, the only thing that can be directly measured experimentally is the gravitational waveform, and this is in the strong theory.
So it looks like the relaxation method, like initially takes some more time, but because it scales better, at some point it is faster than the matrix method. What like simulation time does that take hold where it is faster?
Yeah, that's a great question actually. So here in this time scaling problem, you're right. If I just use this, at some point they would cross. But actually, this plot might be a little misleading. And here I really wish that I had the plots that we have for the simulation one, but again, you can check on the thesis. But the idea is that because the relaxation method is it basically depends a lot on the initial guess that we use. And here, I'm just starting the initial guess as, using the same initial guess for all cases. But the good thing about the simulation embeddings is that the embedding result from the previous time step is actually a really, really, really good initial guess for the other one. So what we see in our simulation runs is that the relaxation method is really fast for improving like small scale results, whereas the matrix method is really good at changing large scale features of the circuit. So like for purposes like I'm showing here for test cases, you're right, the relaxation one can be much more time consuming, but for simulation runs, we actually see that many times the relaxation method is much more efficient because it makes much better use of the initial guesses.
Okay, I have a sociological question. So, spec is this huge open source code.
It's not open source, but yes, it's
Oh.
a huge one.
Oh,
It should
okay.
be open source, but.
But you have changed it in two ways.
Mhm.
Which is the canonical spec, and who decides what is the spec and what is an imposter?
That's a good question. So like spec specifically is it is controlled within the SXS collaboration, so you can only contribute to the main code if you're part of the collaboration. Of course, you can always create different branches of that. You can just copy the code, and if you're in the collaboration, just copy the code and create your own version. But what we call the spec code is whenever you're finished doing a research project like we just finished, we then try to merge our results onto the main code, which is run by like some people usually at Caltech, and that's actually the person that I'm going to be working with in the summer. So basically, he and some other collaborators basically decide what goes into the main code and what doesn't. Does that answer your question?
Okay, so
Big meeting
what
every week.
has the matrix method been incorporated into the main code? Has the relaxation method been embedded in the main code, or are we still waiting?
So far we have only implemented them in our version of the code, because for actually making this merge, we need to clean the code and make it actually good. For usually, as you know, for scientific purposes, we always try to make the code as messy as practical. And so we still need to take some time to just make sure that the code is good enough to put in the main code. And actually, at the conference that I went to a few weeks ago, a lot of people were interested in having this method in the main code, and that's something that we're also planning for the future.
Thank you.
Thanks for the question.
Maybe one more quick question, if it's quick.
I feel bad, I asked two questions. There's two people in the front too.
Go for it, Joy. When you were talking about like pushing the current horizons past embeddability, you showed like two different shapes. One was like kind of like a square, and the other one like a ring around it or whatever. Depending on like which method you use. Is there like a reason why like each method calls each like this special shape, or do you think it just happens?
Well, my understanding for this is that it's just because of how each method is implemented. Like the relaxation method is usually trying to solve for, it's very optimal for solving for small scale features. So like if we already have some initial gas that's right here, it's just going to try to decrease the poles as little by little. Whereas the matrix method is usually really good at like making big changes in the horizon. So like if we have some initial horizon that's spherical, then it's going to jump down and maybe jump up and things like that. But I don't know if that's the best description of it, but basically this is just the results that we see from both methods, and this is actually the reason why we did this, to understand how each method behaves at each in different scenarios. We have a better explanation?
Okay, let's thank our speaker again.